Hello, ME-410. So if you're watching this video, it's because you're thinking seriously about doing the CFD mini project that's posted on Canvas instead of the conventional or original plan for Quiz 2. So this video is going to give you a crash course walkthrough of setting up and analyzing a similar CFD problem using StarCCM, and hopefully it'll help you get all the resources you need to go ahead and run that project. Okay, so in this CFD convection demonstration, we're going to look at a problem based on the concentric cylinders geometry that shares a lot in common with the actual assignment for the CFD mini project in ME-410. So as a bit of motivation for this example, if we revisit this problem we talked about at the beginning of the semester about these so-called parabolic trough solar collectors. So these collectors are set up such that they've got this curved parabolic elongated dish, and that's got sunlight coming in, and it's going to basically mirror, or the mirror on this is going to reflect that sunlight towards a narrow central tube. And the arrangement of that central tube is as follows. You've got an inner tube that is generally painted black, and it's carrying some fluid you're trying to heat up. And then concentric with that, you've got a larger glass tube that allows sunlight to travel through it. And the space between those two is normally evacuated so that you don't have any convection mode of heat transfer for heat loss from that inner tube that you're trying to heat up. But let's just imagine, for example, that maybe there's some defect and a little air or some fluid gets into that gap. How would the convection heat transfer between the inner tube and the outer glass cover behave? So here's our geometry here. So we've got this inner tube that has dimensions Ri, and it has temperature TH. And then around that we have an outer tube, which let's pretend that's concentric, and that has dimensions and temperature TC. And between these two, if gravity is pointing downwards, then the air in that gap will be warmed up by the inner tube. So essentially you'll have a natural convection upwards, and then warm air that's rising towards the colder outer tube, you'd expect that to start sinking downwards. So you'll get essentially some sort of natural circulation pattern that's occurring between these two tubes, where essentially you're getting some kind of recirculation where it's rising towards the inside and it's sinking around the outside. So the question we want to answer is summarized as follows. We want to predict the natural convection heat transfer coefficient that characterizes the heat transfer between the hot inner tube in such a geometry that's concentric with an outer tube at a different temperature. And for just kind of making this problem a little different and interesting, let's imagine that annulus gap is filled with water. So our situation is we've got a 10 millimeter radius inner tube, 20 millimeter radius outer tube, and then we've got the inner tube at 350 Kelvin, and the outer tube is at 300 Kelvin. So we'll start by sketching this out. So we've got the following situation. Gravity is pointing downwards. We have these two concentric tubes, and we're going to treat them as being very long. And this one has radius Ri, the outer one has radius Ro. And let's just kind of think this through here. So because we've got a very long tube, we can say that the flow pattern that's going to develop in here, we might expect it to be independent of the z direction. So essentially, if this is a very long tube, there shouldn't be end effects. So we could say that if this is in the xy plane, then we could say it's a 2D problem in x and y. Okay, next, looking at this problem, we could also observe that we've got a constant inner wall temperature, a constant outer wall temperature, and we could approximate this then as being a steady problem because we don't see anything changing over time. Now there might be some instabilities that lead to sort of oscillating wakes or separation around this tube, but I think as a starting point we could approximate this as being steady. Okay, next, if we look at this domain, it's actually symmetric around the midplane. So we could say that this is going to be symmetric around that center line drawn here. So that gives us another way to simplify our problem. So this is going to be a symmetric problem around that center line. And next, let's just make an assumption here. So this is a natural convection problem. So the flow that's going to develop here is going to be driven by the density changes due to temperature changes in the flow field. But if we assume that those density changes are relatively small compared to the actual average density of the fluid, as we would expect for water, which isn't going to change too much in density over the temperature range, we can use the so-called Boussinesq approximation. So when we do that, we could basically say the following, is that this is essentially treated as a incompressible constant density flow with a source term that just represents the force due to buoyancy. We don't know, strictly speaking, whether this is going to be a laminar or turbulent flow. We haven't really said anything to work through that, but if you work out the Rayleigh number for this flow, based on the definition in the textbook for how you analyze this particular flow arrangement, so we could argue that the Rayleigh number, it's going to be like on the order of 4 times 10 to the 5th. So that's high enough that you would expect natural convection flow in a gap, but not so high that you would expect turbulence. So this would suggest that this is probably going to be a laminar flow. So at this point, we have another choice to make, which is, do we want to account for the variation of the various fluid properties through the domain with temperature? And for now, we can approximate the properties as being uniform or independent of temperature. So we'll say, let's make an approximation that the material properties are all constant. So we're going to say that these are all constant, and we're going to evaluate them at T film. So we'll say that we're going to evaluate them at TF is equal to TH plus TC over 2. And at this point, I think we have all the assumptions we need to simplify and describe this problem. So we can now just write out the governing equations here. So we have, because we're calling this flow as being incompressible, we have the incompressible continuity equation. So since it's a 2D flow, we have du dx plus dv dy equals 0. So that's for our continuity. We have the x and y momentum equations, and we'll write those as a vector form. So for the steady flow, we can write the following. Rho u dot grad u, this is the vector form of that equation on the left-hand side. So this is going to equal minus grad p, the pressure force, and then we have the buoyancy force, which is going to be plus g beta t minus t naught times rho, and here g is a vector. So essentially this is going to be, and this should be negative. So in other words, well, if where the fluid is hotter, you'll have a force pointing, a lower density fluid and a force pointing against gravity. And then we have that viscous term here. So we'll have mu times del squared of u. And this is the vector form in the xy direction. So that was our momentum equation. And then finally, we'll have our energy equation that we can write out. So that's going to be rho Cp u dot grad T for a constant property fluid. And that's going to equal, there's no heat source in the domain, so we just have now the diffusion of heat. And again, if we say constant properties, that's K del squared T. So that's our energy equation for our laminar, steady, incompressible flow. Okay. Next, let's set up the simulation domain, or at least sketch out the one that we want to model. So recall that we are using a symmetry argument here, so we only need to model sort of half of these concentric tube-in-tube arrangements here. So we've got this arrangement here. So we've got gravity pointing down this way. This is a symmetry plane, so those two boundaries of our domain are symmetric. And then we've got the inner wall, so we'll say that the inner wall here is a no-slip wall, and it's at temperature T is equal to TH, which is uniform. And then on the outer wall, we have that as a no-slip wall, and it's at our cold temperature. We now have basically in that domain uniform fluid properties here. We're going to have a few material properties that we're going to need to list out. So we have the density of the fluid, mu, specific heat, thermal conductivity, and because we've treated this using the Boussinesq approximation, we also have beta, which is the volumetric thermal expansion coefficient. And for these various properties, we'll look them up at the film temperature. And we can do that later using EES or some other table or software. Let's get started on setting this case up in StarCCM. So first of all, fire up our simulation software here. Okay, so this is our main screen in StarCCM. Let's start by making a new case that we're going to run this simulation on. We can set this up different ways, but since we're expecting this to be a relatively low complexity 2D problem, we can probably get away with a serial simulation rather than needing to go parallel. So we'll just leave that on and hit OK and let the server get started up here. So before we actually go into setting up the case, which would begin with the geometry, I'm actually going to go down here to the Tools menu in the pipeline here. And I'm going to go under Parameters, and I'm going to start to set up some parameters that will reference while we're working on the problem. And that way, if we want to change anything or use these in other formulas or calculations, they're all available right here at the single place, and they aren't defined in multiple places throughout the code. So let's start by setting up the parameters for the geometry here. Okay, so we've got Ri is the inner radius of our inner pipe. So let's put that in here. So this is units of, or dimensions of length. So for this one, our inner pipe is going to have dimensions of radius 10 centimeters or 10 millimeters, and then we'll have another one for the outer tube. We can set up while we're at it the temperatures of the inner and outer wall that we're going to need later. Before we get any further, this seems like a good time to save, and you should save frequently as you're working through your case. So now that we've got that set up, let's jump into the geometry here. So we're going to start by making a new CAD file or a new 3D or a new drawing for our domain. So since we're planning to do a 2D problem for StarCCM to handle that correctly, we have to draw our geometry on the XY plane. So let's select the XY plane here and make a sketch here. So let's set up this concentric tube-in-tube geometry in the XY plane and actually make this physically anchored here. So let's go through a couple steps here. I'm going to select this inner point and we're going to fix it so that way these aren't floating around in space. We also want to say that these two concentric circles or semicircles are going to sort of cross this center axis here. So I'm going to make this vertical line here, and I'm going to set this as construction, and I'm going to make this point a midpoint on that. Okay, and now I can start setting up some of my dimensions here. So for the inner tube, I can put a radius in, and I'm going to call that, let's see, Ri. And then we can do the same for the outer tube. We actually flip them here. So this one we'll call Ro. So this way, by using this method, we're going to lock them to the original parameters that we set in the top level version of the simulation here. So let's just see how well our case is set up if this geometry is locked in. So if I turn this status indicator on, it's going to tell me which geometries are, or which parts of my geometry are fixed. So if they're not fixed, they'll be in a different color, but right now they're all black, which means that this is a fully defined geometry here. So we're good to go. Hit OK. So now we've got this sketch representing the cross-section of symmetry portion of this annulus geometry. So we'll right-click here and extrude it to make it into a solid. Since we're doing a 2D problem, it doesn't really matter how thick we make this. So we can just kind of make this arbitrarily thin, whatever, 1 millimeter, doesn't really matter. And we can hit OK. So now we've got a physical body, a solid region where we can simulate the geometry here. So we can update the CAD and close out of here. And again, we'll save our problem. So now we have our physical model set up. We don't see anything yet here in Star because we don't actually have a scene. This window is just kind of empty. So to visualize this, let's create a geometry scene. And then we'll take this 3D CAD model and turn it into a part. And now we should have a part visualized here. I need to make a new scene since I made the geometry, or made that into a part after I set up the initial geometry here. So you can see this is our body. And again, let's save that. So now let's go through and define the different boundaries for this semicircular annular domain. So by default, all of the surfaces around this body get defined or grouped as a single set. So they're just kind of all combined together in a single combined surface. So let's now break them up into subsurfaces so we can apply different boundary conditions on each of them. So I'm going to start by splitting these by angle. So if I hit that, I'm going to break this into a few parts. So we can see here, this is the outer wall that's identified here. So I'm going to call this outside. We get the inner wall here, which somehow seems to actually be combined with the two sort of straight symmetry sections. So we're going to split this one up by patch. So if I select this patch here, I can see that that's just coloring in the inner tube there, or inner wall there. So I can separately name that inner here. So I'll make that a separate patch. So now I've got this default 2, which is these two symmetry sections here. So let's rename those something that'll be a little bit more useful. So we'll call that symmetry. And then we've got inner, outer, and then for the two flat faces, it doesn't really matter what we name them because we aren't actually turning those into boundaries since this is a 2D problem. So we can go ahead and save this here. And under the operations, let's make a new, let's set this up to be a 2D problem. So we have to take that part and badge it to be a 2D mesh as opposed to a 3D part or 3D domain. So once we do this, we can run that operation, and what it's going to do is it's going to take the two planes that are parallel with the XY plane and treat them differently so they aren't treated as regular boundaries. And you can see they're marked differently here. So symmetry, inner and outer, are treated as regular boundaries, and then these two are special boundaries for the 2D version of the problem. Before we actually turn this into a region that we're going to set up the simulation on and define the boundary conditions, we need to select the physics that we're going to use to model this transport problem in this domain. So under Continua, let's make a new physics continuum, and then we'll open this up and select our models. So we'll start with setting up the dimensionality of the problems. This will be a 2D problem. We can next select whether we want this to be a steady or unsteady problem. So we'll set this to be a steady state simulation, and we're going to basically solve for the flow pattern and heat transfer that would occur at steady conditions in this domain. We can set our material type next. So we could model this as a gas or a liquid. Since we're modeling this as an incompressible flow, essentially, we don't need to worry about the unique compressibility trends of gases. We could really use either one, but let's just call this a liquid for now. And we have different ways to represent the flow or solve it. So the discretization that I think will work best for us is the so-called coupled flow approach, where the governing equations for momentum, continuity, and in our case energy will be solved simultaneously. And since we've got a natural convection problem where those interact in a complicated way, it'll be a bit more stable to use this approach. Next, we have a choice for the equation of state we're using for our fluid. So we'll call it a constant density fluid. So technically we do have a variation in density because it's a natural convection problem. So as the fluid heats up or cools down, it changes in density and that causes some buoyancy. But the amount it changes is so small that we don't actually need to represent it in the more precise way. We can treat it as having constant density with a body force representing buoyancy that varies throughout our domain. So we'll set it to be constant density. We'll treat it as being a laminar flow, so let's assume that we are operating in a range of conditions such that the flow that develops is not going to really reach a turbulent range. So we'll set it to be laminar here. We do need to solve for the heat transfer in that domain since it's a natural convection problem, so we'll turn on a coupled energy solve. And then we're going to turn on what we're calling the Boussinesq model. So this is a technique you can use in some natural convection problems where you can argue that the variation of density with temperature only shows up in the buoyancy force that results, but it doesn't actually affect the momentum or other general nature of the flow, so we can simplify some of these natural convection problems with that approximation. So let's turn on the Boussinesq model here, and I think we're good. So let's now expand out the models and just step through some of the settings or choices that show up there. So we've got the Boussinesq model, nothing to do there. We're treating the fluid as constant density, again using the Boussinesq model to account for the buoyancy force due to temperature variations separately from the overall density of the fluid. We're modeling this with the coupled approach, so the energy equation is solved together with the flow equation. In the flow, we've got a implicit integration that doesn't really matter so much for a steady problem, and then we're discretizing it to be second order convection, which is a fine choice now. The gradients, the standard choices here are generally fine with how the gradients in the domain are discretized. The one modification I'll usually make is I'll turn on this TVB gradient limiting, which causes a little less dissipation and it'll maybe give us slightly faster convergence as we refine our mesh for the flow solution. Okay, we've got gravity turned on, so that's going to basically allow us to have buoyancy flow. We've set it to be laminar. Here under liquid, we have our fluid properties, and they default to water, but they don't default to water at a particular temperature. They probably default to the properties of water at room temperature, which is not the best description of our problem. So what I want to do is I want to step through and plug in these different fluid parameters to at the film, calculated at the film temperature between the inner and outer wall. So we've got density, viscosity, specific heat, thermal conductivity, and this volumetric expansion coefficient that we need to define. So to get those, you can get them from different sources. I'm just going to quickly write a little EES program that will spit out these material properties, and I can plug them into StarCCM. So let's do that real quick. Okay, no unit problems, and these values all look about what I expect them to be, so let's go ahead and plug them into StarCCM here. And I'm going to set these up as parameters so that I can also use them in post-processing if I'm so inclined. Our material properties defined as parameters there. So let's hop in and plug them in for our material properties. We set up our fluid properties for this problem. Just stepping through the remaining settings here. So it's set to be steady. We're running this also as a 2D simulation, which has to be set up in the XY plane for star. Next, we'll look at the reference values. So we've got gravity set as minus 1g, or essentially minus 9.81 in the y direction, which is the matches how we've drawn our geometry. So that's good. We can go through, there are a couple settings in here that are sort of upper limits for properties. We don't really need to worry too much about them, but there's like this maximum absolute pressure. We could just put a number that's somewhat above 1 atmosphere. We'll set our minimum temperature to be in the ballpark of conditions that we're studying, just so if the iterations kind of start to drift away from that momentarily, we'll not get so far out of our desired conditions. Our reference temperature is here. We'll set our minimum absolute pressure limit to be like, I don't know, 50 kPa, just so pressure doesn't drop too below. Shouldn't be a problem here. We'll set our maximum temperature to 400 K, and our reference pressure is 1 atmosphere. Okay, next we've got our initial conditions here. So initially we have 0 gauge pressure in our domain. Our static temperature, or our temperature, is initialized to 300 Kelvin. This is fine, since it's kind of within the range. That's the essentially outer wall temperature, and initially we have 0 velocity. So this is all good. Next, let's set up a physical region that we'll actually be using to solve in, and we'll set the boundary conditions in there. So we're going to create a new region. It has physics 1, this initial set of physics that we specified here as the physics model applying there. We need to set a body that we're going to solve in, so that's our body here. Next, we'll go through and set up our boundaries for this domain. So if we go back up to the body in the geometry tab, we can go through these one by one. So for the symmetry, I'm going to make a new boundary. We'll call it symmetry. And we'll also create boundaries for the other 2 groups of surfaces. Okay, so now let's step through these boundaries here. So for the symmetry plane, we're going to set the type of boundary condition there to being a symmetry plane, and that's really the only thing we need to set there. For the outside surface, we'll call this a wall. We'll step into the physics conditions, and under the thermal specification, we're going to set this to be a constant temperature boundary condition, and the temperature that we're going to set, we'll call this the cold temperature. So that's a parameter we've defined as TC. And then for the inner wall, we'll also set that to be a wall with a thermal specification of a constant temperature, and that constant temperature is going to now be TH. Okay, so let's save this case here. Now we've got the boundary set up, we've got the domain set up, and we can now set up the meshing here. So we're going to make a new mesh, and we'll call it a 2D automated mesh type. And we're going to mesh this body. You can use different meshing strategies. The polygonal mesher is often a good choice, and we'll say a prism layer is additionally applied in there. So that's going to allow us to have thin cells along the inner and outer walls, which will allow us to resolve essentially boundary layers that are going to develop in this problem better than you can with the coarse bulk mesh. So we've got this set up, and now we need to go through and set some of the parameters for the meshing. So let's go here to the default controls. So first thing is the base size. So that's essentially a size that we're going to use for a reference dimension or reference length scale for the cell sizes, and all of the other options within the meshing are kind of connected or scaled based on that. So we can make this connected to the physical scale of our problem to make things a little bit easier to begin with. So if I bump this out here, I can set up a little formula to relate that base size to length scales in the problem. So if I say that our length scale is equal to that gap width, that's RO minus RI, and it's a fraction of that. So let's start with 0.2 times that. So in other words, our base cell size will be 20% of the length between the inner and outer wall. Or actually, let's make it a little bit smaller just to start with. Let's say 0.15. Okay, so we have that set. We can step through these. We've got our target surface size. Our minimum surface size is limited to be 10% of that base size. If we step through these, I normally like to dial down the growth rate so that the cells don't jump up in size too rapidly as we're working through this. So I'll just turn this to a user specified value of like 1.05, so a slow growth rate. Let's begin with 2 prism layers. That seems like an okay starting point here. So these are going to be thin cells that are near the walls of the domain. And I don't like these to stretch as much as they do, so this is a normal ratio between each layer of that prism layer. So let's dial that down a bit. And let's set the prism layer total thickness to be a constant quantity. So let's make this essentially a fixed quantity that is going to be a fraction of that gap size again. So let's say that this is going to be related to RO minus RI. And we'll say that our prism layer, or the boundary layer essentially, or the thin cells near the walls, are going to be 10% of that gap, or 15% again, seems like a reasonable choice. So essentially our mesh will have these thin aligned cells near the inside and outside, and then unstructured cells between them. So let's create this mesh. And you can see it here because we were looking in the geometry scene. To see the mesh that we generated, let's go to the mesh scene here. And you can see that this is a relatively coarse mesh, pretty straightforward to, or it should be pretty quick to solve, but that's good to start with to make sure our problem is even working, and we can quickly verify whether we have a good solution. So let's save here. So just to recap, we have set up our geometry here. We've set up the physics that we want to solve in there. We've set up the region and the boundary conditions, and the initial conditions are all set up there. What we have also done is we've created this mesh. So we're almost ready to start running the case and solving it, but before we do that, I want to go and set up a couple things ahead of time. So to analyze this problem, what we're trying to do is we're trying to predict the heat transfer coefficient, or essentially the thermal resistance accounting for convection between the inner and outer wall of this domain. So to do this, or track that as the simulation is progressing, let's create a report that's going to tell us what is the heat flux, let's say, on the outer wall of this domain. So we'll go under Reports, and we're going to create a new report, and we're going to do a surface average report. And we'll call this Q flux O for the heat flux on the outer wall. So the quantity that we're going to be averaging on that surface is going to be the boundary heat flux. So we're going to take the average of the boundary heat flux on that outer surface of this domain, and we're going to evaluate it on that particular boundary. So under regions, that's going to be the outside boundary. So what we can also do is we can create a monitor and a plot from this report. So the monitor is going to be printed, that value will be printed at each iteration of the solve, and then the plot will be updated by default at each iteration. Okay, so right now this plot is empty. Okay, next, while the case is running, it'll also be nice to have a couple scenes here that we can use to see how the temperature and velocity fields are evolving. So let's make a new scene, which is going to be for the temperature field. So this scene here, we'll call this temperature. And for that scene, we'll go under the scalar here, and we'll say our scalar field, the field that we're going to show is temperature. And then right now there's nothing there because we haven't actually set the temperature yet in the domain. So what I can do is I can initialize the solution with the initial conditions. So now the whole domain will be initialized to the initial temperature of 300 Kelvin. And now I can do the same thing for a second scalar field that I like to see, which is also the velocity magnitude field. So we'll call this second scene velocity. And let's do the same. So we'll say that the scalar that we're going to show here is velocity. And in particular, we want the magnitude of velocity, not the components of velocity, although you could also plot those as well. Those are listed down here if you want the directional components. Okay, so that's also initialized to 0, which is fine. So now we've set those monitors and renderings or scenes up that will update while we're solving. So next thing we can do is we can go and look at how the solver itself is set up. So that's going to be under solvers. So it's a steady state solve, which is fine. And we'll go to this details for the specific solver that we're using, and we're going to make a few tweaks here. So this is going to be a coupled implicit solve. So we're solving the energy, momentum, and continuity equations simultaneously. And there are a couple settings that we'll use. So this one is an CFL parameter, and it basically says for each iteration in this steady state solve, how far or how many cells out will be considered when it's sort of calculating the interactions between quantities in the neighboring cells. So the default values here, in my opinion, go a little high. Let's cap this at like 100. So essentially, it'll initialize with a conservative CFL value of 1. If for some reason it wants to go down because it's taking a long time to make each individual iteration, it will go down to 0.1, and then it can potentially go up to, well, let's add to 500 here. Okay, next we're going to set up relaxation. So this is essentially only applying a portion of the exact update that the solver would identify at each iteration. So the lower we make this number, the smaller the changes will be to the solution fields at each iteration, but also the more stable the case will be. So let's set this to 0.1, I think is a probably safe starting place. For the linear solver, I also like to dial down the convergence tolerance to be stricter than what it chooses. So we'll set that to 0.01. Okay, next we can take a look at the stopping criteria. So since this is a steady state problem, it will run until some criteria are reached, which indicates that the solution is converged or that you've run it as long as you wish to. So by default, it's set to only run for 1,000 iterations. We don't necessarily need that, but let's just disable this. And instead, we're going to run until our residuals get below a certain value for the different fields we're solving for. So we're going to go new monitor criterion. So we'll add one for continuity, that's mass conservation. We'll add one for energy. We will add one for the x momentum equation, and then we'll add one for the y momentum equation. And now let's step through these. So for continuity, we want to get this residual below a certain threshold, and we're going to set this to be an AND condition, meaning that all 4 of these residuals must be below a desired threshold to be considered a fully converged solution. So our minimum limit here, let's be a little bit more conservative than the default, 10 to the minus 6. Essentially, this case will keep running iterations until the reduction in all of these 4 residuals have reduced by 10 to the 6 relative to their initial value that was identified in the first few iterations of the solve. We should all be set up now, ready to go. Let's pull this all the way down. We see our cases set up here and saved recently, so let's begin the solve. We've initialized our problem. This is the velocity field. We can look at the temperature field here, and let's run it. So we see our residuals are starting to tick down. We see some velocity field developing, and you can sort of see that there is fluid that is rising around the inside, and then it's going to sink around the outside wall. You can see in the temperature distribution, we're hotter on the inside, colder on the outside, and you can basically see this progression developing. We can see that our residuals are working their way down. A good sign is that all of 4 of our residuals are kind of decreasing together. Sometimes you see one of them increasing, another one decreasing. But if they're all coming down together, it means that you're probably converging on the correct solution for your mesh and case setup. If some of them are going down and other ones are going up, you might need to adjust your convergence criteria perhaps to be a little bit more conservative to get to a good solution. But we're getting pretty close on most of these. We can also look at this heat flux monitor plot, and a good sign here is that all of our residuals have gotten to small numbers. And if we look at the monitor plot, it's kind of suggesting that the heat flux is really not changing too much. And you can kind of see here in the output here at each iteration that the heat flux is really not changing to the first 4 or 5 decimal places, which suggests that we are well converged here. So now we have a solution. So it's essentially for this initial mesh, we predict this much heat transfer from the inner to outer wall. That's a good sign. But we still have only solved this on a very coarse mesh. So let's save this and now see what happens if we start to refine our mesh and see how that affects our solution. So if I go back here to our case setup or our mesh setup, and what I want to do is I want to systematically refine this mesh. So in other words, I want to increase the number of cells or reduce the size of the cells in a consistent way everywhere in the domain. So because all of our parameters regarding the sizes of the cells that are allowed in different regions are connected to the base size, what I can do is I can go in and adjust my base size to, let's say, being 1/2 of the size that I had used in the previous iteration. And then similarly, I want to make my cells in the prism layer 1/2 the size they were, or essentially instead of having 2 cells in the prism layer, now I want to have 4 cells in the prism layer. So I've essentially doubled the number of cells in each direction, or essentially taken my mesh resolution and doubled it. So this was our original mesh. Let's run this with our new mesh, and we can see that we've doubled the number of cells in the prism layer and also reduced the size of the cells in a pretty consistent way in the core of the mesh. So let's continue this simulation now. And you can start to see the finer resolution is starting to become apparent in that solve, or in that velocity contour, and also in the temperature contour, which is as we want. We can see that when we made the adjustment to the mesh, the residuals went up because the solution was mapped from the coarser mesh to the finer mesh as we were solving. But now they're all coming back down, and in general, all the residuals are reducing together, which is a good sign. And we've now reached that same threshold that we defined earlier. If we look at the heat flux monitor plot, we see that while there was a bump when we adjusted the mesh, we've now gotten back to a similar value. So we went from like a value of like 19,458 to a value of like 18,595. So a change of a few percent, but not a dramatic change. But the question is now, if I keep doubling the mesh resolution, will this keep dropping down by the same amount, or will it stop changing, meaning that we've achieved a mesh-independent solution and essentially a sign that we have a fully converged solution? So let's save this and double up that mesh again. You can see that now our mesh is even finer, which is a good sign. We can see that the cells aren't jumping dramatically in aspect ratio when we go from the film or prism layer region to the core, which is also a good thing. So let's kick this off again. So we can see your residuals jumped up, but now they're working their way back down as desired. We can see the temperature distribution here is now getting a bit smoother, and we can see a little bit better resolution of the flow here. The velocity field we can also see is starting to get a little cleaner. And let's watch our calculation tick down a bit. Based on all of our residuals kind of coming down together, I think we can probably speed this up a bit by adjusting the relaxation factor a bit. So let's go from 0.1 to 0.15. Hopefully that'll allow our case to converge a little faster. You can see a little bump in the slope of these residual trends, and now we're making slightly bigger adjustments at each iteration. So if you're impatient, you can also use the rather than a constant relaxation factor, we can do this line search, which is going to try to find the optimal relaxation factor that won't destabilize the simulation. The default settings here are a little touchy here, so I'll lower the minimum explicit relaxation factor, and I'll also lower the maximum one, and turn off verbose. We don't need to see that each time. So now every 10 iterations, the solver is going to try to update the relaxation factor to reduce the residuals without destabilizing the solution. So you can see now that we're at our maximum limit for that relaxation factor, and we're taking a much faster convergence. Okay, so let's look at these here. So we went from 19,457 to 18,594 to 17,488. So we're dropping by about a heat flux of about 1,000. And we're still maybe not 100% converged on the, at least for the heat flux here, but I think there's a sign that if we, we aren't really getting into the desired asymptotic range, that this is, relatively speaking, a similar order of magnitude change in this residual. So that to me suggests that we might need to go even finer on our mesh to really demonstrate convergence. Let's also make these criteria a little stricter, just because it looks like our solution is still changing a good bit in terms of that heat flux. So if on our residuals, these three went to 1e to the minus 6, let's drop those a bit stricter to allow the solution to converge a little further. Something that we want to see so that we know the heat flux we're reporting is a pretty well converged quantity, and it seems to be here within the first 4 or so decimal places pretty well converged. Okay, so our residuals are still dropping significantly, or our heat flux is still dropping significantly from one mesh to the next, so that means we need an even finer grid. So let's go back and update the mesh another time here. Try to get an even finer grid here. So hopefully we're now able to converge a little bit better. Okay, so now we are once again pretty well converged. We see that the heat flux is pretty constant to the first few decimal places, 3 or 4 digits of precision, and we see that here the value went from about 17,480 to about 17,300 some. So it dropped when we did this systematic refinement by about 1,000 from here to here, and then it dropped only by about 100 from here to here. So that's a sign that our solution essentially, as we doubled our mesh, we got a much smaller change in that heat flux. That's a good sign that we have achieved a converged solution here. So now we have essentially a converged heat flux for this problem. We also can see the velocity flow pattern here, where you get this rising hot fluid around the middle that then floats upwards near the center line and then sinks around the outer wall, and we have this recirculation pattern. It's also evident here in this temperature plot. So now that we have a solution for this heat transfer from the average heat flux on the outer wall, let's see how that compares to the value that you would predict using the correlations or heat transfer models, let's say from the textbook. So this is a natural convection problem, so let's pull over EES and take a look at this case. So we have our material properties listed here already for our problem. So we've got our temperatures listed up there. Let's start by setting up the heat transfer analysis down here. So we have our dimensions as follows. We have Ri is equal to 0.01 meters. Ro is 0.02 meters. And for this particular problem with heat transfer through concentric cylinders, we're going to use a model that's listed in the textbook, and for that particular problem, there's a kind of unusual length scale that's used. We're going to use equation 960 for the length scale. length scale for the problem. Let's just run this, update our dimensions, set our guesses. Okay, next let's calculate the Rayleigh number for this problem based on that same length scale. So it's called RAC in the textbook. Okay, so we have a couple more parameters. Let's set their units. And we see that the Rayleigh number calculated here is like a few 100,000, which is in the range where you would expect natural convection, but also not high enough in the millions or so where you'd start to see turbulent flow. So it's also in the range listed for validity of the particular heat transfer correlation listed in the textbook. Okay, now let's calculate the heat transfer correlation, and the way it's defined is based on an effective thermal conductivity. So in other words, it's defined such that the natural convection is treated as just increasing the effective thermal conductivity of the material in the gap rather than with a regular heat transfer coefficient, and that way you don't have to worry about different heat transfer coefficients whether you're using the inner or outer tube diameter. So let's plug in their formula. Get our effective thermal conductivity here, okay? So this is in watts per meter Kelvin. So no unit problems, good sign. Save, update our guesses, save again. Okay, so finally, let's compare this to the heat flux that we predicted for the natural convection simulation that we ran in StarCCM. So let's see how these line up. We're looking at the heat flux on the outer wall basis. So we have Q prime, that's heat transfer rate per length of the pair of concentric tubes, is equal to 2 times pi times that effective thermal conductivity. And then our heat flux for the outer wall is that Q prime divided by the perimeter of the outer tube. So let's see what we get. So here the heat transfer rate per length of tube is 2682 watts per meter, and then on the area basis of the outer cylinder we get 21,340 watts per meter squared. So if we go back into StarCCM and line that up, we were seeing a heat flux of about 17,314. So that's like 20% low or 15% low. Not crazy far off, not crazy close, but within the range of expected variation maybe between a correlation like this, which was developed for a wide range of conditions, and you might only expect on the order of 10 to 20% accuracy depending on the case that you're looking at. So this is a pretty good comparison, pretty good sign that we're in the right ballpark. We don't see perfect agreement, but also good sign that we're able to get in the general ballpark that you can get with this kind of simplified 2D steady simulation. So let's wrap that up here. So hopefully this is a nice walkthrough of how you can set up a CFD simulation of this kind of natural convection problem in StarCCM, run it, solve it, and get a useful heat transfer calculation that hopefully is in the right ballpark or comparable to the values that you would get from established correlations, and you could trust it to give you reasonably plausible solutions for problems of interest.